Yes, of course.
So I can start. Good morning. And I would like to thank the organizers for. Oh. Okay. Okay. So thanks a lot for organizers for the invitation, and it's really great their kind of courageous step to organize something in these difficult times. So I will talk on neutrino physics in the COVID era. This is the outline. First, neutrinos in the standard model plus mass of neutrino. Then neutrinos and beyond the standard model. I will discuss anomalies and connections and possible inference of these. Then I will focus on neutrinos and new physics at the low energy scales, kind of the area of active research in the last years. And then I will comment on masses mixing and flavor symmetries, trying to have some assessment of the present day situation. Massive neutrinos and the standard model. So this is what we know. We know that we have very well tested standard model plus mass of neutrino. I'm not saying left, right neutrinos, or just mass of neutrinos, which actually were obtained through oscillations and adiabatic conversion from different experiments. Important point is that new physics beyond the neutrino mass can be actually introduced in such a way that the feedback of this new physics onto standard model is very weak, so that we are just left with neutrino masses, not even knowing what is the nature of neutrino mass. And actually, there are several possibilities that can be Dirac neutrino mass. It can be Majorana, for instance, through D5 Weinberg operator. But it can be effective mass, which is generated by interactions of neutrinos with medium, for instance, with dark matter. And I will comment on this later. So this is the summary of analysis of all experimental data. This is a recent paper. And a few things to mark. One is that normal ordering is somehow 2.5 sigma is preferable. So red is inverted and this is normal. Now, we have CP phase, which is now closer to pi, and deviation of 2-3 mixing from pi over 4 is smaller. So all the things will have some impact on the future studies. One should mention that the data become more consistent, analysis stable, and this group gives results which are quite similar to what a new fit, another group, is giving. So the data agree actually with hard mass and no dependence of mass on energy, environment, it has been observed, which is very important. Actually, test to understand what is the nature of neutrino mass. The question is if there is any tension inside this global field. There are two things quite recent. One is that so-called solar Cumulent delta m squared to 1 square tension disappears. The recent results from Super Kamiokande and also SNO plus now observe some distortion of the spectrum of events, which actually is consistent with what is expected. And then day-night asymmetry at Super Kamiokande is reduced from 3.3 to 2.1%. That leads to the shift of the best fit of delta m squared from solar neutrino data to upper values. So it's like shift like this. And now kind of difference of the solar neutrino and Cumulent is something like 1 sigma. So that essentially anomaly disappeared. The second one, and actually Albert has discussed this a little bit in the lecture, there are new results from NOVA and T2K on the phase, on the CP violation phase, delta CP, and this is 2-3 mixing. So there are two different points. One is from NOVA here, which is something like 0.82 pi, and another one T2K, which is close to minus pi over 2 maximal CP violation. There are some speculations that this difference can be explained by different baselines in these two experiments, as well as matter effect, since T2K has much smaller distance. This difference can be reconciled by introducing non-standard neutrino interactions or sterile neutrino, which has been discussed in a couple of these papers. There is no tension in the case of inverted hierarchy. However, another interpretation would be that if you just make joint analysis, you will get something which is close to pi somewhere here. And this is a result of global fit. You see, it's this is the best fit point, which is not far from pi, and even closer in this analysis. It's actually bad news for future experimental measurements of CP asymmetry, because if pi, there is no asymmetry at all. Now the question is, suppose this is correct and the phase is very close to pi. So why do we have a difference? Why CP phase is large in quark sector and not in lepton sector? And there's quite old idea how it may happen. So can CP be close to pi? That can be obtained in a straightforward way if you assume that a PMNS matrix is the product of two matrices. Actually, I will come also to this later. One is of the order VCKM, so the same close to CKM matrix, multiplied by something new, which may originate from, say, dark sector, from right-handed neutrinos, whatever it is. So if you then say that CP violation comes from VCKM and of the same order as in the quark sector, and there is no CP violation here, and actually that can be obtained if this matrix is of so-called bimaximal or tri-bimaximal type, which is very popular, which you can get easily from symmetries. And then what you will get this relation between CP violation in leptonic sector and in the quark sector, which is quite big. This sign is big, of the order of 1. So you have this 1-3 mixing here, multiplied by sun delta. Here is you have 1-3 mixing in quark sector, which is very small. This is VUB. And this is 2-3 mixing in lepton sector, which is something like 1 over square root of 2. So this is of the order of lambda, if this is Kabiba angle. This is Kabiba angle cube. And you will get that mixing angle in quark sector is automatically of the order of lambda square, which is very small. So which means that delta CP is either this minus delta or pi plus delta, and delta is in this ratio. So that leptonic CP is small because leptonic 1-3 mixing is large. There's a lot of activities, in fact, in the theory of neutrino propagation and oscillations. I will not even repeat what is written here. And surprisingly big activity here. I will just mention one aspect of this, and this is the coherence and decoherence. So in configuration space, the coherence means that wave packets which describe propagation of the mass states separate because of different masses and different group velocities, and sigma x is, say, the width of the wave packet. In the energy momentum space, it is just averaging over uncertainty in energy in your setup. So these two results, the coherence results in suppression of interference. And actually, these two descriptions are equivalent because we have connection between sigma x, the size in the configuration space, and inverse uncertainty in energy here, or uncertainty in the momentum. So what we introduce coherence lengths, which is the sigma x over difference of group velocities, and group velocity is just a differentiation of Hamiltonian over p. So in vacuum, this is the difference of group velocities is proportional to delta m square or to energy squares. And so you get the coherence length, which is proportional to sigma x, the size of the wave packet, and energy square over delta m square. There's a recent paper where people tried to actually extract information on sigma x on the size of the wave packet from reactor experiments. So what do you expect? You expect the averaging effect. Therefore, the absence of averaging or decoherence means that the baseline is much smaller than coherence lengths, and this gives you the upper bound on the size of the wave packet, which is the baseline of the experiment, delta m square over 2 energies. So what you see here, the analysis of Diaby and Reno experiment, and without any coherence, decoherence, you would have this green line. Decoherence leads to smoother curves, and you see here the curves for different sigma x. And this is for Camland, which is even more sensitive because the baseline is bigger. So the bottom line analysis gives that sigma x is something like, should be bigger than 2 × 10⁻11 centimeters. So I made some estimation that expected sigma x in this reactor experiments is something like 10⁻9, still quite far. But one can work in this direction and maybe get some interesting results. Maybe some additional mechanisms of decoherence exist. Now, what we did is to study coherence in matter. In matter, the group velocity changes, and therefore the coherence length changes. What is interesting that in matter, you may have infinite coherence lengths, so that your neutrinos will just propagate and oscillate forever. There is no averaging effect. And that corresponds to equality of the group velocities. So in matter, you may have equal group velocities of eigenstates of propagation, although the masses are different in vacuum. And therefore, there is no separation of the wave packets. And you see here the ratio of coherence in medium over coherence in vacuum, the lengths, as a function of energy. And you see at certain energy, this ratio becomes infinite. This is in the constant density case. So actually, this resonance is close to usual MSW resonance, and it coincides with resonance for mass states. Another important thing that at very high densities, actually the coherence length approaches again the things which are in vacuum, in spite of big densities, which is important for supernova neutrino. So what are other situations when you have infinite coherence? One is when you have the density profile periodically modulated. So in one half of period, you have that one state propagates faster, and another period, another one faster, and so they kind of catch up each other. Another interesting example is Castlevale Profile, which to some extent imitates situation in the case of supernova. So you have the density profile of this type. And again, you have even several points, several energies in which the coherence length becomes infinite. So this is number of periods when you keep the coherence. And you see there are several energies which actually at which you have infinite coherence. And they more or less close to so-called parametric resonances. Again, so that actually result is important for it has some applications for supernova neutrinos. Now, neutrino anomalies, and I will discuss some anomalies and their status. One is the reactor neutrino anomaly, which actually states that the present-day observations made at different baselines distance is these rates are smaller than what is expected according to Huber-Muller predictions, which are based on Grenoble spectra. So Grenoble actually measured the energy spectrum of electrons of different isotopes, and especially uranium and plutonium, and they converted this energy spectrum of electron to energy spectrum of neutrino. Recently, it was some measurement in Kurchatov Institute of this ratio of uranium to plutonium, which is important ingredient in these computations. And what they have found that the measured ratio is below of what Grenoble experiment did. And so this means that if this result is correct, that just anomaly is absent, because it's this ratio for Grenoble is I think it's opposite, right? So this R for Kurchatov Institute is smaller, and this precisely, almost precisely, reproduces the observed ratio. So new measurements actually they reduce the expected flux, and therefore anomaly disappears. Now, there are several experiments indicating different, neutrino oscillations, and in particular, it was NEOS experiment and DANS experiment, which last year actually indicated the same delta M square, which was interesting, and some people became excited. Oh, it's not just one experiment indicates some delta M square oscillations with certain delta M square, but two experiments. And things changed because NEOS did a new analysis, and now they have delta M square 2.37 electron volts, while DANS experiment, this Russian experiment, it gives 1.3. So it's like, you know, the question is, do you have what? Do you have oscillations or fluctuations? And what is important, that oscillatory curve with two free parameters, delta M square and mixing angle, always gives better feed than just constant. So they reproduce better the fluctuations. So it seems there is nothing here. And I will not comment on neutrino 4, even Albert did want to comment. This is something which actually contradicts to everything. Now, mini-boon and LSND, so they observe the excess of E-like events in comparison with what is expected. And this is dependence of this excess on L over E distance over the energy. Now, LSND are this green, and the other points are mini-boon for in neutrino and anti-neutrino channel. So a few things to mention here. The best fit line corresponds to maximal, essentially, mixing, which is excluded. So 1 sigma deviation corresponds to sine squared to theta 0.01, which is also strongly disfavored. And oscillation interpretation nearly excluded by disappearance of data. I don't want to go into details of this. What I should also to mention that you see in these data points, there is no oscillatory curve. You don't see it's just a smooth lines. And therefore, you can actually try to explain these results, not by oscillations, but by some other mechanism. And now it's popular game to produce some kind of effective theory, and now in this case, effective theory of mini-boon excess. So what we have protons which hit target, then something propagates, and then in the detector we see one shower events, electromagnetic shower events, which could be electron, could be gamma, E plus, E minus, or two gammas, and the mini-boon experiment is not able to distinguish this, and there is no, of course, big separation between two tracks. Now, what also we know that there is a correlation in time of the heat and protons delivered in bunches here, and appearance of this shower in the detector. And the difference in time just precisely corresponds to the velocity of light propagation of the system, which is behind this black box, and therefore is consistent with very light neutrinos. all the mechanisms which actually require introduction of heavy enough particles can be excluded or strongly restricted. So the masses should be quite light. Now, what is inside this black box? Inside the black box, we have production via mixing or upscattering of usual neutrinos, or mixing with usual neutrinos. Then propagation, then decay, then upscattering of new particles. And now let me open this black box. And there's a kind of plenty of possibilities. You introduce new fermions or new bosons. Let me show you something. Here what we have, proton produces pi and k mesons, and then in the decay of pi and kaons, you have production of new neutrino state, which propagates and produces in the detector shower, for instance, due to electromagnetic decay. Now, this is another mechanism when you have, again, production of a new neutrino inside the decay pipe. Then this neutrino decays into electron neutrino, which then produces usual E-like event. Or like here, where you have your neutrino, which actually first decays into boson, which then produces shower events, for instance, just E plus, E minus decay or gamma decays. There's another set of these possibilities when you have muon neutrino produced here, and then muon neutrino upscatters produce new particle. Or like here, this is in detector, here is in the between of detector and the pipe, or like here. So you have muon neutrino, which produces new particle inside the detector, and this new particle decays through B, etc. So here you see the number of points of interaction increases, and you can make classifications as usually produce as much different models as you want. Now, using this scheme, you can predict number of events in some other experiments like T2K, like Minerva, Nova, Nomad, using front detectors. So, and this configuration is quite close to what we have in Miniboon. So the way you proceed is the following. We know what is the excess of events in Miniboon. Using scenarios, which I have described, you predict a number of events in a given experiment of a given type. And here we see some results for this near detector of T2K. So what we see here are predictions as a function of the lifetime here of heavy neutrino. And these are prediction ratio of, actually, okay, so this is predictions of number of events. And what you see here, the upper bounds, this is 1 sigma, the 3 sigma, clearly this scenario, which is A, which corresponds to one of the diagrams before is excluded. This is excluded in some range of lifetimes, and here is also excluded using Minerva data. So that actually excludes many possibilities, and with some other analysis, so practically everything is either in kind of tension or already excluded. So good news is that this GSNS square experiment in Japan start to operate. And this is the experiment which aimed to just repeat LSND result. Pi and decay at rest, distance is something like 24 meters. This is the detector. And they will just study this new mu bar to new E bar transitions and oscillations. Then, of course, you know, there's a rich program of studies of neutrino oscillations in Fermi. But here is just direct test of LSND result. Neutrino and other anomalies. There's big activity in studies of neutrinos and dark matter. And there are different ways how neutrinos can be connected to dark matter. So right-handed neutrinos themselves can be the dark matter particles. Or so dark matter particles can participate in generation of neutrino mass. The same symmetry can be responsible for smallness of neutrino mass and stability of the dark matter. And what I will discuss a little bit is that refraction on the dark matter can produce effective mass of neutrino. Now, there are other connections, mass of neutrino with G-2 or the B anomalies, and so there's plenty of papers studying this possible connection. And the game is to use, of course, effective field theory and proceed in the following way. You first write all possible, say, operators constructed out of particles of the standard model. which violate lepton number by 2 units if you want to produce Majorana mass of neutrino. Then if you closure these lines, like for instance here, with 2 Higgs here, fields, this is precisely D5 operator, which generates neutrino mass. Or you can move in opposite direction. You can open this box, or this circle, and to see which kind of interactions are normalizable you can introduce to reproduce this operator. So this gives you new interactions and new particles, which can actually contribute to these anomalies, RK, RD, G-2, and simultaneously give UV completion of your operator of generation of neutrino mass. So now it's machinery. It's really no need even to have kind of artificial intellect to do this job. So I don't think that I said this is what I'm saying, but now we can do model building without model builders. So there are programs which actually produce for you all this, realize this program, and you get finally which particles you need, which masses, etc. Now, in addition to what I have described before, and people focused on this type of dimension 5 operators with Higgs boson here, it was a recent paper which actually reminded us another possibility that even in a standard model, we have some other vacuum expectation values, not only Higgs. We have chiral symmetry breaking, and actually we have condensate of quarks, quark-antiquark pair. Why not to use these? And so they actually tried this type of the diagram, which can be produced by so-called dimension 7 operator. You see here lambda, and this is lepton doublet Higgs, and this is quark structure, which actually then condensate. Now, the mass of neutrino has this expression, and for 300 MeVs for the condensate, you need to have a lambda of the order of a few TeVs. There are a few issues, of course. If you introduce these more complicated operators, so what you do with these, you need to suppress this. Oh, sorry. Otherwise, of course, this will be dominating. Here you have a Higgs wave. And of course, the issue of UV completion of this stuff. But anyway, one should remember such a possibility. Now, neutrino physics and low energy scales. So all these years we worried about some high energy scale desert, which is something like 14 orders of magnitude here. So this is mass scale. This is the scale around 1 GeV, where our particles are living, the standard model. So we were worried, so what happens here? And just ignored, say, 40 orders of magnitude desert below the standard model scale. So what we have here, what we know is 1 over lifetime of the universe, then the bound on the rate of proton decay, which is somewhere here, possible bound on the mass of the photon. That's it. So now we started to populate this area with various things like axion-like particles, like dark photons, etc., etc. Well, the question is, of course, there is some hierarchy problem here. So how about hierarchy problem in this case? What is interesting that we play, what is important, that we play here with very small couplings when we go to small scales, and that actually saves us from various problems. So that's a general scheme we are working. We have standard model, we have probably neutrino portal, Higgs portal, and then a lot of stuff here in the dark sector. Well, actually, neutrinos probably provide the link because their scale is somewhere in between the standard model scale and something what happens below. Let me just show what's going on in the very simple example. And so let's take just interaction of a neutrino with some new fermion, which could be right-handed component, and the scalar field. Actually, that started already a long time ago to trying to extract some information from this type of the interactions. So G is effective coupling, and there is quite stringent phenomenological bound that G is smaller than 10 to the -7. And this type of the interaction, because this is doublet, the charges on here are singlets, this fermion on F, so that can appear through the right-handed neutrino portal, what we are saying. So through right-handed neutrinos, you can introduce such an interaction with small couplings. It's interesting, it's simple, but it has a very rich phenomenology for light particles. So we can have new effects in refraction. And what is important that this effect is actually proportional to g squared over the mass of mediator squared. And therefore, when you reduce g squared and mediator, this effect doesn't disappear. So that can actually generate effective mass of neutrino. Or with this, we can even produce bound neutrino system, like bound stars, clouds, etc. Let me give you one example. So here, what we have the background formed by fermions with some asymmetry, which is given by epsilon. So fermions, antifermions here. So example is relic neutrinos, for instance, one of the examples of such a situation. So n is number densities of these fermions, and we have two diagrams of scattering. We have neutrinos scattered on this side of this dark matter particle. This one is a resonant diagram. It has a resonance here, and the effective potential, which is generated by this diagram, is written here. So Y here is just energy over energy of resonance energy. So everything. So resonance, there is a resonance here, and the resonance energy is the mass of the mediator square over the mass of the target. This stuff. Now, what else is here? The gamma, the width of the resonance is extremely small. In many cases, it can be just neglected. So G is 10 to the minus 7. There's another version when you have bosons in the background. And let me just show some results of computation. This what you see is the potential generated by diagrams, which I have shown, or V0. And let me again remind what is V0. V0 is here is G squared over the mass of the mediator square. And this is the number density of the background. This is essentially the strength of all these effects. Weak charge. No, it's there is no current. This is a scalar interaction in the size singlets of the standard model. Oh, so this is what I'm saying. It's not just direct. This is effective coupling. So what you have coupling with right-handed neutrinos. Of course, you have Higgs boson, which break the symmetry, and then this new guy mixes with right-handed neutrinos. Yeah, no, so this is how the potential looks like. So this is zero energy as the function of energy. So it starts from some value, then it goes down quite far, then go up. And actually in the resonance, this refraction of the potential is precisely zero because it's given by real part. And in the resonance, the amplitude becomes imaginary. Then it go up and then it go in this way. Okay, so that's the general form. Like this, and then like that. And so these are different curves correspond to different asymmetries of the background. I don't want to go into big details. Now, what we can introduce, we also introduce vacuum contribution, which is delta m squared over 2 energies. And this is also, we can introduce resonance vacuum contribution, which is delta m squared over 2 energies in resonance. So just to confuse the reader, we introduce this dimensionless couplings, which is always kind of nightmare to see. But anyway, the potential has such a form. Now, this, what we can do, we can include this vacuum term and sum it with this potential. And I will tell you why it is important. So this is what you see here, dependence of medium potential plus vacuum term, which is delta m squared over energy, or again, this V0, and dependence like this. So this go up, so we start from low energies, it go down, then and go up, and then like this. So what is interesting, so why people haven't studied this before, essentially? The point is that usual Wolfenstein potential doesn't depend on energy. It's just constant. But it is constant because the mediator is very heavy. So in the case of standard interactions, we are in the regime where the resonance is too far. I mean, so it's glacial resonance, essentially. This is where we can see some probably effects. Probably I will skip because this picture actually changes structure of usual MSW matter resonances, which are the potential is given by this expression, some new resonances appear, usual resonance shift, and this actually can be used to search for these new effects. But what I want to say, you can introduce so-called effective mass of neutrino, and this is how it is introduced. Effective mass of neutrino is 2 energies, and then the sum of the potential. So effective mass square includes this medium effect, just enough to say this. And here you see dependence of this effective mass delta m square over usual one is the function again of energy. And it repeats to some extent behavior of the potential. Changes with density, it go up, and then it go in this way. So this is the resonance energy. This type of effect has been used to explain mini-Boon results. So all this kind of discussion is just for these applications. So what we are saying is the potential increases very quickly. It becomes very big at certain energies near the resonance. This means that the oscillation phase induced by this potential also increases and becomes very big. And so what you see here, if you have short baseline experiment, then usual phase is very small. The effect is very small. However, if you meet the resonance in certain range, then the phase becomes big. And so this is how the oscillatory factor depends on energy. So this is essentially sine square phase over 2. And normally what you have is very small effect if you have LSND and no sterile neutrinos. But in certain range near the resonance, you have big phase and therefore oscillation effect. So in this way, you have strong oscillation effect in very narrow energy range. And that was proposed to use to explain mini-Boon access by scattering of neutrinos on the relic neutrino background. Of course, you need to have very big densities of this background. This is for a different baseline. This is 0.55, 5.5 kilometers, 25 kilometers. But the structure is like this. These are usual vacuum oscillations dominated region. And then this is due to this anomalous refraction effect. Well, this is badly excluded. And it is excluded by the following fact. So we have effective mass square, which depends on energy. So what we extract from the experiment, not vacuum mass, but we extract this delta m square effective. What is interesting that at high energies, potential behave in the same way as mass term. It's 1 over E, and it's kind of generic feature. And therefore, you always can confuse if you have real mass term or this potential. And so what you see here, delta m square effective as a function of energy. So here's like a vacuum, and then it has this peak. But above the peak, you have something which is like the mass, but differ from vacuum delta m square by this some coefficient R. And so what actually mini-Boon needs, it needs this coefficient R to be bigger 1.6. So this is how it is introduced. Delta m square effective is R delta m square. And here you see the experimental data points where delta m square was extracted. So what you see here that no energy dependence of delta m square has been observed in very wide range of energies, from reactor energies to ice cube and Antares. So it's constant. What you would expect if you want to explain mini-Boon is something like this. Well, go down, it go up, and then it's somewhere here because that's already, you know, for 0.17. So this is even 10 times smaller than what is needed for mini-Boon. I want to briefly say that around the resonance, the potential has this 1 over E dependence. And then the question, of course, can you completely substitute neutrino masses by this effective potential, which has the same energy dependence? And the point is that we actually concluded that we observe the mass in, say, SNO experiment or Super Kamiokande, because there is some term in your evolution Lagrangian which has such a behavior, 1 over E. But who told you that this is delta m square over E and not something else like some effective potential? So one is still to prove this. So these are some conditions to have this 1/E dependence. But now let me say the following. The effective mass due to interaction is given by this expression is g squared, the number density of a particle of the background over 4 masses of the background particle. Now what we can say, suppose our resonance energy is quite small, and all this energy dependence substantial we see in the resonance region and below, but above the resonance, we have just usual 1/E dependence. Actually, we checked that there is no energy dependence above 0.1 MeV approximately. So what we know is that this term with 1/E dependence is fine above 0.5, 0.1 MeV. Actually, solar neutrino data have the lowest threshold. So it's enough to put your resonance energy below 0.1 MeV, and then you can explain everything. But there is a problem with cosmology, because now your mass depends on the number density of particles in the background. And in the past, this number density was very big, right? It increases because density becomes bigger. So this is the difference from usual mass, because usual mass is proportional to VEF, and VEF doesn't change with time when you go to early epoch. Here, this is the key difference. And so we have number density which changes in this way. I will probably skip this, some details you can find later. So that's the effective mass, how it is related to the effective local mass, which we see now in our laboratories. There's this 1/Z cubed, this redshift factor. This is the factor which gives you the ratio of local density of dark matter and the average in the universe. And you can use this and account that the effective mass, naively, if it is now 0.05 electron volts at 1,000 Z equals 1,000, is already 5 electron volts, which is actually excluded. So, but one should not forget the following. So this is the overall picture of dependence of delta m squared on energy. It increases linearly. It has this maximum, and then it's a constant. And here we are playing that all our observations are in this range. But below the resonance energy, actually this effective mass decreases. And so if this resonance is also not too close to zero, so for instance, like 0.01 MeV, then in the range of energies of C and B neutrinos, the effective mass is 10 to the minus 5 electron volts, very small. And so it increases, but it doesn't increase so much that you violate the bounds, cosmological bounds. It's bad news for Catherine, because for 1 electron volt energy, the effective mass is 2 10 to the minus 4 electron volt, which is not possible to measure. Few comments on neutrino bound states. There's a long story starting from Markov, who was saying, so why neutrinos are not forming the stars? And he used actually analogy with neutron stars and computed characteristics of these neutrino stars. It's just very dense degenerate neutrino gas. But if you take, and he used actually for masses something like 1 MeV, and that was fine. He has some sizes of these neutrino stars of galactic scale. However, if you use the present very small masses, then you have the mass of this neutrino star, which is 10 to the 20 solar masses, and the radius is close to the radius of the universe. Now, a group of the people used mass of neutrinos in keV from 10 to 100 keV range, and this is essentially a warm dark matter case. This is usual standard gravity. However, if you introduce new interactions which are much stronger than gravity, then you may have something interesting at scales which you want to have. And a series of papers by Stephenson et al. So they use mass of neutrinos 13 electron volts and use new interactions with scalars. And they discussed, again, they get the masses of the neutrino stars like 10 to the 3, 10 to the 8, 10 to the minus, 10 to the 10 solar masses, and the radius 10 to the 13 centimeters. This is solar system size. And they speculated that that may contribute to evolution of of solar type systems. So we revisited this problem just in view of this recent interest in these scalar interactions. And let me just show you some results. So for instance, if you take very big coupling constants at the level of present bound, then these neutrino clouds will have the radius, say, of a kilometer, and this is the central density. So you have funny structure with these neutrino clouds separated, say, by 20 kilometers and the size of 0.5 kilometer. And here you see the density profiles, dependence of density on the radius from the center, and there are funny dependence here. And so that I think if someone is interested, they can discuss this in details. And so this is the last part. And actually, Joe Pineda helped me a lot. So I just dropped many slides, and this is why I managed to finish today. It's a nice introduction to the topic. And you see here many authors which contributed, and I could probably fill in all this slide with authors who are actually doing these things. So this idea to use modular symmetries as flavor symmetries are motivated by string theory, actually these modular symmetries, and the hope was to reduce the number of parameters to make things more predictive and connect masses and mixing. Well, actually, let me make one comment. So our previous approach was precisely to decouple masses and mixing, because it was clear from the beginning that it's difficult to explain this large, or almost, say, double maximum mixing in lepton sector with mask hierarchies. And it was very interesting, actually, an unexpected result that you really can decouple masses and mixing. Of course, you can construct flavor models where these things are connected. But this residual symmetry approach precisely aimed at a different explanation of mask hierarchies and mixing. But it's always the problem to do this. Now, this is modular symmetries. I will probably skip even this slide. And so the whole idea is that you cover couplings are not couplings, but they are functions of this modular field. And at low energy, it just depends on the breadth of this modular field. So it's just constant at low energy. So if you go, of course, to string scale, you will get something else. And so the couplings are transformed in this way, which you saw already before with this kind of new factor, which actually is power of the weight, so-called of the multiplet. These are usual transformation properties. Now, and so this law is determined, so actual dependence of y over tau, or these so-called modular forms, they actually can be derived using these transformation properties. Now, invariant Lagrangian is written here. So what you need to have, of course, symmetry, because of you have this usual raw transformation, like say transformations according to S4 or A4 symmetry. Plus, you need to have this condition, which actually tells you that you need also to keep invariance with respect to this to these factors, which with respect to these factors. So now one can compare this approach with just usual Flavon approach, because here you have Yukawa coupling, which depends on the field. In usual approach, you introduce your usual term, multiply them on the Flavons, maybe in the square and cube, and these Flavons then develop webs. So to some extent, formally, this is the same. So here you have Yukawas, which depend on webs of a modular field, and here you have just webs of Flavon. Degree of freedom is the same, so you can reproduce the same results in both approaches. And the hope was that here is more tough stuff because you have just a single Flavon field, two parameters. Here you have many webs. And here the form of this Y is determined by the symmetry. Here you need to deal with the potential, which is sometimes quite difficult problem. Now, from model building, this is what I'm saying, what's going on, from model building to symmetry building, minimal versions will not work. So then you need to do something. You need to extend. You need to play with more complicated symmetries, with more moduli field. You can play also with the way how you construct finite discrete symmetry group out of a starting continuous starting group which is infinite. So there are various complications. You can use several modular groups. And in the end of the day, it's a question if we are gaining something or not. Or maybe our use of modular symmetry is not correct. And let me come back again to this setup. Maybe it's kind of we fail because you want to explain everything at once. And actually not just a single physics, but two different physics contexts, different scales are involved here. So according to this relation, it actually gives a very nice prediction for S13 mixing. We have a common sector for quarks and leptons, which is this given by VCKM, and I explain this. I call this CKM physics, which actually responsible for hierarchies of masses and small mixing. And there is additional contribution in lepton sector, which probably comes from dark sector of the theory coupled with neutrinos. And this is responsible for large neutrino mixing and small neutrino masses. And here we may have some special symmetries, and maybe even not broken. And we can use here modular symmetries to explain, and what is enough to explain, that this produces a tri-bimaximal or bimaximal mixing. Oh, it's dagger. Sorry. Yeah. So this is one of the examples of this type. We have, say, SO10, and so we have this usual nice stuff. And we introduce 16-plet, which actually provides a connection between visible sector and the dark sector. And it is in this sector we have, say, S4 symmetry. We have here flavons or something else if you want. And it is this which produces for you bimaximal mixing. And then you can reproduce the experimental data. And it is my conclusion. Thank you. So it seems that three neutrino framework works well, fine. So anomalies and tensions are losing their sigmas. And now I don't know what is the anomaly in neutrino physics. So in particular, the case of sterile neutrino become weaker and weaker. So neutrino interaction with light-dark sector has a rich phenomenology. It produces so-called resonance refraction at low energies, a possibility to substitute or maybe partially substitute usual neutrino mass by interaction with medium. You may probably explain some features using this additional contribution. And one should worry, actually don't forget, once you introduce this, you will get these bound neutrino states. The question is, what are the properties of these bound neutrino states? Well, number of neutrinos here is 10 to the 22, 10 to the 25, 10 to the 40, maybe. It depends on the parameters. So, but one should actually check and maybe get even additional bounds or observe something interesting. And then modular symmetries, I don't want to repeat again, is promising. And I think, so we are still in exploratory space. But one should also keep in mind that maybe we apply them in not quite right way. Thank you.
For being precisely in time. So it's not
can you explain fundamental principle or some physics which is standing behind this modular symmetries? Why do you think, I mean, from where they are coming from?
From string theory, string motivated. So that's what actually Ferulio, his idea, and he has papers even with Altarelli, he first asked questions. So we have playing with this discrete symmetry. What could be the origin of these discrete symmetries? And so then they saw what that can come actually from string theory, from compactification. So this tau is modularized. They describe compactification of these extra dimensions. And so to say we have for free, the only what we need to do, we need to create, because the group is SL2Z. This is what actually the symmetry of this moduli by definition. But then we need to create the finite group to have this explanation of mixing. It's like A4, S4, and
In this possibility to use the interactions with the medium, you do not break lepton number, right? So the
well, it depends. You can so in the simplest version we don't, but you can also break
masses in that.
It depends. Yeah. So this is the simplest version.
So I'm intrigued with your mechanism of infinite coherence. Usually the story is the coherence not only for neutrinos with wave particles and masses, also for wave optics, and it's related to the fact that the resolution of the energy, as you already correctly measured, is infinitely small, so that you can have infinite coherence. But in your case, you say you can have infinite coherence with a delta E, with, let's say, with an uncertainty in the energy. Is that what you are claiming here?
Yeah, this is okay. So eventually you are doing, of course, integration over averaging. So this infinite energy, infinite coherence is, so to say, for certain energy or certain energy.
You have delta equals 0. Okay.
Yeah.
Okay, good. In the Coherence matrix, delta CP. Now, as you know, you can actually obtain the value of the strength of CP violation in electronic sector by measuring the sides of a triangle. I think even you worked on that, right?
Yeah.
Now that we have better data, can we just deduce from the data and knowing the size of the triangle, knowing the area, therefore you knowing delta CP? You even work on that at some
point. Yeah, so but I have not updated, so I don't know what is present day. I think in so
that's the most fundamental.
All right,
way.
so we have this. We contributed to this neutrino factory book with Yasaman Farzan, precisely on this triangle, and in that place we put kind of. And projecting onto future this triangle. So there's answer to your question. So I suppose in 20 years we will have better measurements and how it will look like. Yeah, so there is some.
At the moment, it's not enough. Is that what you're saying?
Well, we know. So you can reformulate in different ways. So we know what we know. So it's kind of 2 sigma to 2.5 sigma evidence for CPU violation. But now it's even weaker because it depends how you analyze data. If you use NOVA and T2K, and you make some kind of joint analysis, you will have something close to pi, which means that there is no CPU violation. And the fact that you can of course do this in terms of triangle, but the answer should be the same, of course.
Sure.
So we can still take 2 questions. Maybe I will start with your question first, and then say your question will just follow.
Sorry, one remark. When you discuss masses, you want to separate masses and mixings. Now, one thing about neutrino masses, we don't know if they are that hierarchical. It might still be that we are in the what's called the degenerate phase, where the difference in masses are small with respect to the average phase mass, and therefore, in that case, it's relatively easy to get very large mixings when you are close to degeneracy.
No, vice versa. I think if you have degeneracy, that's easy to get large mixing.
Yeah, that's what I was saying.
Yeah.
Sorry.
Yeah.
In that case, so we shouldn't be really surprised in that case of the large mixings, unless we think that the neutrinos are really almost zero and heavily split. And we had some model with Maxim Libanov and others where we had some kind of Frogat-Nielsen scheme which comes from 6D. It corresponds to Frogat-Nielsen, and indeed you get 2 degenerate neutrinos, which by rotation it gives a kind of a pseudo-Dirac system. The mass of one neutrino is opposite to the mass of the other approximately, and therefore the what I think is very interesting parameter, which is the effective mass in Neutrinoless double beta decay, gets heavily suppressed. And so this is a different situation where, on the contrary, the mixings and the masses are intricately linked.
No, my comment was on the previous approach of these discrete symmetry groups. And especially this approach with residual symmetries was developed to completely to disentangle this. And actually, it's an interesting feature which is based on mixing is given by relations between elements of mass matrix. Okay, so mass splitting and doesn't depend on the absolute values. So, for instance, you want to you need to have element 2, 2 equals to element 3, 3 or something like this. And that gives you the mixing. And it doesn't depend, this relation do not depend on absolute scale. So that, I think that was kind of amazing development. But now we want to go back and we want to use these modular symmetries. Well, I should say that the simplest modular symmetries give something which has no big hierarchy. So if you just take this, and now they are struggling to reproduce big mass hierarchies. So now they introduce this sophisticated some special points or some cancellation to have hierarchy.
Okay, last question.
Yes, Alexei, thank you for the talk. How many, in your opinion, how many years with all the ongoing experiments, is it realistic to expect this ambiguity of the inverted and the degenerate and the normal hierarchy to be clearly resolved?
Well, so what people are saying that we need to wait Dune and Hyper K, which means it's till the end of 20, when they start to operate. So they probably need some years to operate. 35, yeah, 200, yeah, 2035. Who knows how to think. Well, you know, I'm very kind of upset that some projects like Pingu and Orc are so slowed down. So I think things will be developed, but then there's kind of social phenomena which actually. Well, Juno, you see, Juno, now they have probably 3 sigma. And they say, okay, we need to combine with Orca to have more significant results. So now that's, and I don't know what eventually. So I don't think that Juno will solve really kind of final the problem.
Okay, so let's stop the discussion on this subject. Thanks a lot once more for your interesting talk. Today is Professor Studenking. He is going to present us an overview of neutrino electromagnetic properties. So please go ahead.
Thank you.
Change your slides with this. Yeah. Join. Yes. Yes. Thank you. And then let's Where? No, to maximize the window. Okay, and now you can share this green. This is the token. Okay. Yeah, and I'm waiting it again. Okay. It's all the slide. Okay. Again? Mm-hmm. No, we have to open it again. Maybe the first time. Yeah, the PDF is better. Better from it's the same. Yeah. If you would prefer the PDF, it's this is the PowerPoint. Yeah. And then you share. Okay. Maybe share the whole screen instead of this. Yeah. Mm-hmm. Okay. Really? Yeah. Okay. And now, think about your slides. Yes, thanks. And slides, so you know how to perfect. And then just move it. Okay. But two arrows. Yeah. And pointer is one more.
Okay. Well, I'm sorry for this delay. It is really a great pleasure for me to be here, and I'm thankful to Judge Zapanas and the organizers for invitation to come to this famous summer institute, Corfu Summer Institute, for the workshop. And this is really the first time I am participating in person in the conference since I think February 2020. It's a quite new experience and quite new feelings. So I'm going to give a short review on routine electromagnetic properties, and we shall start with some reminders on some introduction to the theory. Then we shall deal with constraints on the most important neutrino characteristics, electromagnetic characteristics, which are the neutrino magnetic and electric dipole moments, neutrino Mili charges, and the charge radio from laboratory experiments. Then we shall deal with neutrino electromagnetic interaction with astrophysical environments, and also consider the astrophysical probes of neutrino electromagnetic properties. And in final part of this presentation, I will deal with some new effects in neutrino oscillations that first are due to electromagnetic properties of neutrinos, and in addition, which are not electromagnetic by their nature, but they reproduce results very similar, mimic the results that can be expected from as manifestation of neutrino electromagnetic properties. So the most complete among the recent reviews of the subject can be found in our joint paper with Carlo Giunti, published several years in Review of Modern Physics, with the title Neutrino Electromagnetic Interactions, a Window to New Physics.
and there are several updates. I would also like to mention two papers published during recent months, also reviews on neutrino electromagnetic properties, and in particular on neutrino magnetic moments and neutrino Milli charges. Well, excuse me, how to move this? Do you know? No. Okay. Well, there are some advantages in the conference organized online. So a person can participate in several events at the same time. And now in the TAUP conference that is running, we have 9 presentations devoted to neutrino electromagnetic properties. So if we really believe that neutrino is a massive particle, then we should very seriously approach the question of neutrino electromagnetic properties. That can be described by the so-called neutrino electromagnetic vertex function, which from some reasonable constraints imposed by Lorentz covariance and electromagnetic Gaussian invariance can be composed or distributed and in 4 form factors, which are the real electric, the dipole magnetic and electric form factors, and the anapole form factor. So, and from hermeticity and the behavior of electromagnetic current under discrete symmetries transformation, we can further specify the properties of neutrinos, electromagnetic properties. And here we just come to the conclusion that the Dirac and Majorana neutrinos exhibit quite different electromagnetic properties. In particular, for Majorana case, from CTP invariance, it follows that only 1 from 4 form factors can be non-zero. And this observation dated to 1939 to Wolfgang Pauli. So, and here we conclude that in principle, the study of neutrino electromagnetic properties, we can use this as a tool for distinguishing the nature of neutrinos, whether it's a Dirac or Majorana particle. In some more general theoretical framework, we can consider the vertex function between the neutrino mass states, and in this case, the vertex function as well as form factors are matrices in neutrino mass space. And again, Majorana and Dirac neutrino exhibit quite different electromagnetic properties. Well, if one considers form factors, if considered neutrino interaction with real photons, then form factors reproduce the static electromagnetic characteristic of neutrinos, for instance, the magnetic moment of neutrino. So it often claims that electromagnetic properties and in particular magnetic moments of neutrino open a window to new physics. Well, indeed, in the standard model for the case of massless neutrino, magnetic moment is 0. And if we suppose, and if we know that mass is not 0, that even in the easiest generalizations of the standard model, we get that magnetic moment of a Dirac neutrino is not 0, and it is proportional to the mass of neutrino. If we put the numbers corresponding to the present Katyn limit, we get that magnetic moment is something 10 to minus 19 Bohr magnetrons. It is a tiny value if we consider it in respect to the present experimental constraints on these magnetic moments from reactor, neutrinos, and from astrophysics. Many orders of magnitude between this easy generalization of the standard model prediction for magnetic moment and the present constraints, experimental constraints. So now I would like to flash to laboratory experimental constraints on magnetic moments, charge radius, and Milli charges. It also included to the table of particle properties published regularly by particle data group. Well, I would like to underline once again that so far there is no any indication, no from experiment in laboratory in the Earth, neither from the astrophysical observations in favor of non-zero neutrino electromagnetic properties. We have only constraints. There is one exception, xenon. I will just comment on later on about this. So most easily accepted from theoretical point of view and the most well studied theoretically and experimentally is for sure the magnetic moments of neutrinos. The studies of neutrino electron scattering provide the most sensitive method for experimental investigation on neutrino magnetic moment. So the cross-section contains the standard model contribution and an additional term that derives the possible non-trivial neutrino electromagnetic properties, and in particular is proportional to the effective magnetic moment squared. So it is often claimed that it is possible also to incorporate to this cross-section the charge radius of neutrinos just by shifting the vector constant, adding this contribution due to charge radius. But as we have shown with my colleague recently, this is not exactly the fact. So here is the plot of these two contributions. These dotted black lines, nearly flat, stands for the standard model contribution, weak contribution, and these colored lines are for the magnetic moment contribution with different values of magnetic moment 3, 4, 5, 10 to minus 11 Bohr magnetons. Well, it is easy to see that the lowest, smallest measurement electron energy is, the more sensitive these kind of experiments are to this effective magnetic moment of neutrinos. And the best world limit on with the reactor neutrinos on the effective magnetic moment has been obtained by the JAMA and JAMA collaboration. This is the joint venture of GNR and ITEP, Kurchatov Institute, at the Kalinin nuclear power plant that is located more or less on the halfway from Moscow to St. Petersburg. And this bound is 2.910 to minus 11 Bohr magnetrons. Well, now a new stage of this experiment is running. This JAMA 2, this sometimes they call this JAMA 2, sometimes they call this JAMA 3, but really this is the most exact title of this experiment is New GAN experiment. Just these days, new results from this JAMA 2 New GAN experiment were reported at TAUT, and it is expected with this, within some years, this experiment will provide the sensitivity for the magnetic moment on the level 5 to 9, 10 to minus 12 Bohr magnetrons. So I will skip these descriptions of the experiment. Well, what is very important to note, and what is measured in the scattering experiment, this is an effective neutrino magnetic moment that depends on the spherical position of neutrinos in the detector. And the observable results and implications of these limits from different experiments, which use, for instance, the reactor neutrinos or the solar neutrino fluxes, are in general different. The most comprehensive analysis of neutrino electron scattering, accounting for mixing and oscillations, was performed in our studies together with Kozakov, and we have made several statements, especially related to the charge radius, but I will just fix this later on. So in 2017, Bioregions collaboration published their results for the magnetic moment of neutrino, that is 2.810 to minus 11 Bohr magnetrons. This is the summary of available constraints obtained by different experiments and different years, and all these numbers are included in the particle table of particle properties by the particle data group. It is not excluded theoretically that neutrino can be mealy charged particle, and there are a lot of efforts to constrain this value. Some years ago, I just analyzed the JAMA collaboration data on cross-section and added an additional term, the third one in this cross-section, that accounts for possible effect of neutrino mealy charge. And from the data of JAMA data, I obtained the upper bound for the mealy charge of neutrino on the level 1.510 to minus 12 Bohr magnetrons. And this bound is included to the neutrino properties by the particle data group. With the new set of experiments, New GAN experiments, the sensitivity will be on the level 1 10 to minus 13. This is a prediction for the future analysis of possible future results of this experiment. This is a particle data group. So, and this is a summary of all constraints available now. And the most severe bound on neutrino Milli charge, of course, comes from is level 3 10 to minus 21, comes from entirety of the hydrogen atom. So the charge radio, this is indeed the most accessible for experimental studies as a magnetic characteristic, because of the most closer to the present experimental constraints. The predictions of the theory, the most close to the most closest to the in respect to magnetic moment, and where there is a huge gap between constraints and the theoretical predictions within easy generalizations of Fermi model. So this is about some theoretical framework. So, and I will just go back to our paper where we just analyzed the neutrino electron scattering, accounting for mixing, and also accounting for all possible electromagnetic characteristics of neutrinos. And one of the conclusions was that neutrino charge radius in neutrino electron scattering cannot be considered just as a shift of the vector coupling following this prescription, because there are also contributions from the flavor transition charge radius, but this cannot account for this. Thank you very much. Well, and just using this idea, we, with our Chinese, Italian, Russian collaboration, using the coherent data, obtained the new bounds on the transition charge radius. These results have been highlighted by the editors of ERD and also included to the particle data group the properties of neutrinos. So this is important, importance of the coherent neutrino scattering studies in general. I just skip this. Electromagnetic neutrinos in astrophysics and corresponding bounds. So there is a set of the most important electromagnetic interactions due to that can be important contribution and implications in astrophysics. The first is neutrino, the heavy neutrino decay to a lighter one. The same diagram describes the Cherenkov radiation, this plasma. The same diagram describes the spin light of neutrino. So we predict an effect when neutrino is moving in a dense environment, and due to precession in the classical vision of this effect, due to precession of magnetic moment, neutrino can emit light, and we term this the spin light of neutrino. So there is also the plasma decay to neutrino anti-neutrino pair, neutrino scattering, neutrino spin precession in an external field. And as we have shown, it can be also due to neutrino interaction with transversal matter currents. The spin light of neutrino was predicted and studied in a series of our papers. And in one of the recent papers, we discussed the possibility of visualization of this effect in different astrophysical environments. Well, astrophysical bounds on neutrino magnetic moments. So the most important, one of the most important effects for astrophysics is due to magnetic moment of neutrino is the appearance of right-handed neutrinos. It can be implemented in 3 different ways. So first, the helicity of neutrino can be changed by the scattering on electrons, neutrons, and protons. Then there could be the spin or flavor precession in the transversal magnetic field. And the third one, this is what we have predicted and studied recently, that the spin and spin flavor precession can be due to weak interaction without any electromagnetic neutrinos, without any external magnetic field, due to weak interactions with the environment if matter is moving transversally or is polarized transversally in respect to relativistic neutrino propagation. So, there are astrophysical bounds based on this effect of appearance of right-handed neutrinos from supernovas related to observed duration of neutrino signal. The bound is of the order of 10 to minus 12 Bohr magnetrons. Again, from supernovas related to observed neutrino energies, again, the same bound, 10 to minus 12 Bohr magnetrons. The most stable and the most well appreciated bound from astrophysics on effective neutrino magnetic moment comes from the plasma decay to neutrino anti-neutrino pair. that can increase make more faster the cooling rate change, and this is the bound often named as the best astrophysical bound. This 3.10 minus 12 Bohr magnitudes obtained by first time by Raffelt in 1990. Neutrino radiative decay also can provide bounds, but much weaker from astrophysics, and bounds on the millicharges of neutrinos, again from plasma processes of an implication to red giants from supernovas, and again, as I mentioned, from neutrality of neutron, the most severe bound on millicharge of neutrino 10 to minus 21. So in our papers, one of our recent papers, we consider another possibility to constrain millicharge of neutrino from astrophysics. We studied the neutrino motion in magnetized and rotating media. And this is magnetic field. This is the rotation angular velocity. And we solved this equation for the wave function and obtained the spectrum of neutrinos in such environment that is quantized. There's a double quantization, I should say. First, due to millicharge neutrino interaction with a magnetic field, this is very much like these famous Landau levels for electrons in the magnetic field. And this is another quantization. This is a new phenomena, a quantization of energy of neutrino when it moves in a rotating media. This is an omega rotating frequency of matter. So in classical treatment, it is possible to describe this as the effect of some kind of Lorentz force, which have electromagnetic part and matter part that depends on the rotation and the gradient of density. And just using this, we introduce the so-called neutrino star-turning mechanism. So the fact is that escaping millicharge neutrinos, when they are moving on a circular orbit inside the magnetized rotating star, and there is a feedback of the Lorentz force that can influence the rotation. And from very conservative criteria, just to avoid the contradiction of the impact of this neutrino star-turning mechanism impact on the observation delta pulsars, we get this bound. This millicharge neutrino should be less than 1/10 to minus 19. This is the best, the most strong astrophysical bound, 2 orders of magnitude weaker than the maximal constraint that on this value obtained from neutrality of hydrogen atom. So now I think that I have about 3 minutes. I would like to stop on some new developments in the neutrino spin and spin flavor solutions. And in particular, I would like to advertise a new effect that was proposed in my paper in 2004, that it is possible to generate the spin and spin flavor solutions without any electromagnetic fields. There is no need for magnetic moment, no need for transversal magnetic field, but due to weak interactions in case when matter is propagating transversally in respect to relativistic neutrino motion. So, and this effect was formulated in this paper. The possible emergence of neutrino spin oscillations, for example, from left to right neutrinos owing to neutrino interaction with matter under the condition that there exists non-zero transverse current component of matter polarization is the most important new effect that follows from the investigation of neutrino spin oscillations above. So far, it has been assumed that neutrino spin oscillations may arise only in the case where they exist a non-zero transverse magnetic field in a neutrino rest frame. So, and in this paper, I just calculate for the first time the probability of spin oscillations in transversal matter current, and this is the amplitude is determined by this E effective. If we switch off the electromagnetic part, the remaining part is exactly the contribution from deep interactions of neutrinos with the transversal currents. So indeed, it is possible to produce spin and spin flavor oscillations due to weak interactions with transversal matter currents, or in the case when matter is polarized transversally. This effect was confirmed independently by a 3 group of people. So, and our recent papers with my student, we just developed the quantum treatment and analyzed all possible phases here, and we describe the meta contribution in the effective evolution equation, the meta effect at rest, the meta moving, the magnetic longitudinal and transversal field, and also include non-standard interaction and consider different possible resonances in neutrino oscillations. Thank you. And also study some astrophysical applications of this. So this is half a minute for this interplay between spin and Flavor oscillations that was studied with my student in one of the recent papers. So we consider two Flavor neutrinos with two helicities and in magnetic field, and have found that there is an interplay of oscillation of vacuum frequency and magnetic field frequency. In particular, if you consider neutrino Flavor oscillation, electron left to muon left, we see that the amplitude of Flavor oscillation on vacuum frequency, this is modulated by the magnetic field frequency. And the same is for the spin oscillations. The amplitude of spin oscillations on the magnetic frequency is modulated by vacuum frequency. So this is important for applications in astrophysics where strong magnetic fields are present and matter is present, and it is not possible to consider, if you want to like to solve the problem analytically, these different oscillations separately. So this is I skip. So and just in one of recent papers, I just implement the same when the spin oscillations are produced by transversal matter currents. And this is one of the recent papers. We described the role of CP violating phases in neutrino oscillations, in neutrino, antineutrino, and strong magnetic fields, and have found that indeed the Majorana CP phases induce new resonances. And we predict that can be an additional tool for distinguishing neutrino nature Dirac or Majorana that would be important next high volume detectors like Duna, Kamehameha, and Duna once supernova neutrinos detected. So conclusions, this is the summary of most important constraints on neutrino electromagnetic properties. And a few 15 seconds for these future prospects. So I have already mentioned there is an indication of xenon that the excess of recall energies over the background can be interpreted as a transformation of resistance of magnetic effective magnetic moment of neutrino on the level similar to the Barksina limit. Of course, this should be checked independently. So new improved limit comes from neutrino Centauri analysis. This is 2.2 10 to minus 12. New limit also from the new analysis of deep of red giant branch. And recently we proposed a new setup to observe neutrino observed neutrino coherent stretching, and within this we can test the magnetic moment of neutrino on level 7, 10 to minus 13. So there are some constraints, new constraints from X mass on the media charges of neutrinos. And so just to summarize, the studies of neutrino electromagnetic properties indeed important because it is studies of the property of real particle, and also because it provides a very important insight to fundamentals of particle physics. Thank you.
Thank you, Professor. So the talk is now open to questions and comments. Are there any? There is one over there. Yes.
When you talk about electromagnetic properties of neutrinos, do you mean specifically electron neutrino or active neutrino independent of flavor?
So, in general, this is the most right and straightforward approach, theoretical approach to description of electromagnetic properties of neutrinos is to introduce all these properties in the mass basis of neutrinos. So you have three neutrinos, and each of these neutrinos can be attributed with the electromagnetic properties. Then through mixing, you can transform this possibility of flavor neutrinos to react on electromagnetic environment, or just to manifest electromagnetic properties in scattering on electrons, neutrons, and protons. But of course, we always start with the mass basis. This is the discussion probably that was raised yesterday by Alexei, because the flavor neutrinos are very good for experimentalists, because the Lagrangian of interaction is most easily understood in the flavor basis. Yeah, but if you consider particle, if you attribute a mass, you can attribute mass to flavor neutrinos, yeah, in a normal sense of this, yeah. And of course, if you write a Dirac equation, for instance, of course you should write the particle with the mass, and just you add electromagnetic properties. So then you make transformation with what we did, but not only we, but we summarized the long story of several decades.
I'm afraid we should say, hey, stop this discussion, because we just have this unitarity limit, which is coming from the time of the departure of the boat.
Okay.
We can continue, you see.
Yeah, thank you.
Yeah. So thanks once more, our speaker.
Yeah, thank you.
And we go to the third talk of our session, and this talk is by Professor Valle, and the title is Neutrinoless Pathfinders in New Physics.
Please let's share the screen. Hello, I'm trying to share the screen.
This is the screen you see. Bottom of the
Hello?
Okay.
Do you see the screen?
Yes, very good, very well.
Okay, so first of all, I wish to thank the organizers for their kind invitation. It's a pity not to be present, but we are in pandemic. So my task is to illustrate to you the role neutrinos can play in helping us to make the first next step forward in particle physics. I start from neutrino oscillations. The discovery was made in solar and atmospheric neutrino experiments. These have been followed by reactor and accelerator-based studies, which have not only confirmed the oscillation phenomenon, but also improved the parameter determination. So much so that, in fact, we now have a quite consistent global picture with a good determination of the lepton mixing parameters. These are the leptonic analogs of the CKM matrix elements characterizing the quark-weak interactions. except for 3 points. Namely, we still lack a good determination of the atmospheric octant, of the CP phase, and of the ordering of the neutrino spectrum. You see, you have 2 solutions for normal and inverted ordering. In fact, these loose ends form the target of the next generation of upcoming experiments, but that is should be a dedicated talk, so I will not go in this direction. Instead, I will jump directly into theoretical interpretation, starting from the 3B maximal ansatz. You see, this means that you have bimaximal atmospheric mixing, trimaximal solar mixing, no reactor mixing, and as a consequence, no CP violation. Although ruled out experimentally, the TBM pattern still constitutes a good starting point from where to generalize by exploiting symmetries in a rather consistent and systematic fashion, so as to obtain 2-parameter generalizations, which are not only viable, but also predictive. For example, this one here, you see, it predicts this green band, which overlaps the generic oscillation region within a narrow range of delta CP values, indicating predictivity. However, this is just one out of a broad class of examples I won't enter into. Instead, I will jump into another mixing pattern, namely the bilarge pattern, which exploits the observation that the largest quark mixing angle, namely Cabibo, is similar to the smallest lepton mixing angle, namely Reactor. This way, one can expand the lepton mixing matrix as a product of 2 factors, each of which is expanded in a power series on the small angle, lambda. So if you know lambda, you know them all. Indeed, this is what you find here, the prediction for solar mixing in black and for atmospheric mixing in blue. Again, this is an example out of a class I won't enter into. Instead, I will jump to neutrinoless double beta decay. First, this process is very important because it is associated to the Majorana nature of neutrinos, and it offers the possibility to probe parameters that are inaccessible to oscillations, such as the absolute neutrino mass scale. You see here, indeed, you have the 3 mass eigenvalues present in this amplitude, and also the 2 Majorana phases, which are characteristic of Majorana neutrinos. And notice that I'm using here our original parameterization of 1980 because it is much neater for the description of neutrinoless double beta decay, much neater than the choice made by the PDG. The most favorable situation for having measurable neutrinoless double beta decay would happen if all neutrinos are nearly degenerate or are degenerate. And to describe this situation, I give you a novel description of these M beta beta parameter. Instead of plotting it versus the lightest neutrino mass, I express it in terms of this degeneracy parameter eta, a dimensionless parameter, so that when it equals 1, neutrinos are strictly degenerate. In real life, this is just an idealized limit. One must depart either to the left, that's the normal ordering band, or to the right, the inverted ordering band. Experimentally, we have already the brown band ruled out by the Kamlan-Zen measurement. And in the recent study with these people, we have analyzed the cosmological restrictions, which basically rule out the vertical band that you see here. So altogether, quasi-degeneracy is strongly disfavored. Another possibility, which is rather interesting, is having one of the neutrinos massless or nearly so, because in this case, even for normal ordering, you see here the amplitude never vanishes. There is an absolute lower bound for neutrinoless double beta decay, unfortunately too low compared with these black lines, dashed lines, which indicate experimental sensitivity of the upcoming round of experiments. So we move up to the case of inverted ordering. In this case is much more restrictive than the generic one up there, so much so that in fact all of the points in this band lie inside the sensitivity of the coming experiments. So one can envisage, if this is the choice made by nature, to be able, in fact, to underpin the value of the relative Majorana phase between these two massive neutrinos. What if all neutrinos are massive, though? In this case, there are no guaranteed lower bounds, but they might still be there as a consequence of family symmetries. And there have been many papers. I show you a recent result from this JCAP paper, which shows that, in fact, the preferred value of that particular model lies in the region of, within the sensitivity of the new experiments and also cosmology. Of course, a discovery of neutrinoless double beta decay would be a major breakthrough in our field. First of all, it would demonstrate lepton number non-conservation in nature, and by the black box theorem, which is almost 40 years old, it would also imply that at least one of the three neutrinos is a Majorana particle. This argument is totally general and also useful when probing for lepton number non-conservation at collider energies. Now I move to the origin of neutrino mass. This is the million-dollar question. It was noted by Weinberg 40 years ago that to the standard model, you can add this unique dimension 5 operator involving two lepton doublets and two Higgs doublets, so that when the Higgs goes into its vacuum expectation value, then you have a Majorana mass. But this is far from being a theory of neutrino mass. To go any further, one needs a UV completion. And in fact, most of the art of neutrino model building consists in providing interesting UV completions of this argument. And one of them is the seesaw mechanism. From my point of view, basically because it opens up the possibility of a dynamical understanding of the small neutrino mass by minimizing a Higgs potential. And in fact, the expectation values V1 and V3 associated to singlet and doublet neutrinos, they may actually hold the key to the understanding of the stability of the electroweak vacuum. So they touch the electroweak theory right at its heart. Within a seesaw picture, of course, small active neutrino masses can be induced either by the exchange of heavy right-handed neutrinos or from the exchange of heavy triplets. And these go under the name type 1 and type 2. It's anecdotal here to notice that in our original seesaw paper, indicated here by the cyan color, we called the triplet seesaw type 1 because we were thrilled by its simplicity and also because it was our baby. However, beyond this anecdote, there are important differences between our formulation and the yellow ones. And I show here the yellow seesaw. It relies on left-right symmetry and implies that the number of right-handed neutrinos matches the number of left neutrinos by gauge invariance. In contrast, the standard model-based type 1 seesaw that we suggested, here the number of singlets is totally arbitrary, so that one can have a missing partner seesaw mechanism having only 2 right-handed neutrinos or 2 singlet neutrinos instead of the 3 active ones. And this, in fact, each one could be associated with one of the scales that we have measured in oscillation, the solar scale and the atmospheric scale. And indeed, this provides today the minimum viable type 1 seesaw. In fact, in the old paper, we also noticed that you could have a 3-1 possibility. Notice that in both cases, 3-2 and 3-1, we have a lower bound for neutrinoless double beta decay, as I just described. So you have well, not a guaranteed, but a promising detection prospects for double beta decay. In the 3-1 case, however, there is only 1 right neutrino, so there are 2 missing partner neutrinos, and they do not acquire mass. These are those that would be in the solar sector. So they are degenerate, there are no solar neutrino oscillations. So as it is, this model is ruled out, but it constitutes the template on top of which you can build models where the solar scale is induced by radiative correction associated to some other physics, such as dark matter. This is, in fact, the idea of the Scotto seesaw. Basically, it puts together the seesaw paradigm with the WIMP dark matter paradigm together. This way, one understands the wavelengths of the solar oscillation compared with the atmospheric as a result of resulting from radiative correction. Conversely, one can have a situation with more singlet and doublet neutrinos. Especially interesting one is having double the number of singlets as compared to doublets. So you
excuse me for interrupting. Somebody stopped the recording. Why is that? Sorry. Can the organizers put back the recording? Well, is an organizer of a chair there? Sorry, Jose, I don't know what's happening.
I cannot do anything.
Me neither, me neither. I've just noticed that the recording is stopped.
Yeah.
Maybe well, it's okay. Maybe you can continue. I don't know where is the chair. Maybe we lost the connection. I don't know.
But
I mean, I hear you perfectly. But...
I'm not right now in the room, so I'm watching online. But sometimes the internet drops. Actually.
Yeah. It's the recording was stopped. That's all. Sorry for
interrupting. Can I continue?
I'm not sure if the internet has dropped. And let me check who else is online. Because you're not the host, Jose, and the usual host would have been Zupano's account. So I think the account in the room has dropped the internet.
I see.
It happened a few times.
I mean, online is perfect. We hear it perfectly, of course. But...
It's because everyone in the room is offline, but
and the rest
in the hotel. So
that's right.
So yeah, it's somehow the internet disappears sometimes in the room, so they're blind now.
Albert also knows because he had problems twice.
I see.
Yeah, one problem with me, so I remember it vividly.
Indeed.
Yes.
And it took like maybe 10 minutes to get it back up, right?
Yes, and some went from coffee for in the meantime.
So I should continue, I guess.
I guess. In any case, there we have the transparency.
If you continue, you're continuing just for us on the Zoom session because
I would wait, I guess, till they're back.
Sorry,
but we also do have the boat trip today, so I don't know.
That's the problem. And one more talk online.
Shall I
go on? The boat trip is not our problem, right?
That's right.
It is for me.
All right.
Are you seeing my face? By the way,
you should be at the session.
Are you seeing the video?
Yes, I mean everyone that is on the Zoom session is seeing you. Like Nick, Steve.
Yes.
There's no problem with your talk on the Zoom.
It's just that it's not being shown in the actual room of the conference. Now he's returned.
Okay, now he's returned. Japan is returned.
So I was discussing the fact that the standard model-based seesaw allows for having a different number of right neutrinos as compared to left neutrinos. So I gave the example of the missing partner, and now I move to the opposite situation where you have more singlet than doublet neutrinos. For example, 3,6, in which you have two singlets associated to each active neutrino. In this case, one can go to a limit of lepton number conservation, and lepton and neutrino masses vanish identically as they do in the standard model. However, lepton flavor and leptonic CP symmetries are violated despite the neutrinos being strictly massless and degenerate. And this is very interesting, not only conceptually, but also practically, because it means that mu3 gamma can exist in a theory with massless neutrinos. And therefore, there are no constraints that follow from the neutrino mass, from the lightness of neutrino. On the other hand, this massless template constitute the building floor for constructing low-scale systems. All one needs is to have a small lepton number violating blob, you see here in red, in the singlet sector, and it's transferred to the normal active neutrinos through the exchange of this heavy quasi-Dirac mediator, which, however, can be accessible to collider energies, such as those of the LHC. So you have masses induced by accessible mediators and protected by a symmetry. In fact, the symmetry protection can be a double one, to the extent that this red blob may itself result from yet another layer of calculable physics. For example, here on the right, you have the dark seesaw case, where this blob actually is the dark sector. The dark matter will be the lightest of the mediators, of the hidden sector mediators, contained in the blob that will provide the neutrinos their mass radiatively through the inverse seesaw mechanism. It's a very interesting, very elegant mechanism. Has been recently accepted to PLB. Now, so much for Majorana seesaw. Now, you can also seesaw a la Dirac. And this is an example to the left of Dirac type 1 seesaw. And in the right, you have also two examples of dimension 6 type 2 seesaw. It's dimension 6 and dimension 5. So again, the story is the same. The symmetry protection is the key thing. But here the symmetry protection should be a double one. First, you should protect the smallness of the mass. Then you should protect the Diracness of the mediator. In this case, this is a recent model in PLB, where the mediator of small Dirac neutrino mass lies at the Pechequin scale. Now I turn to flavor. This is one of the sectors where the standard model fails miserably, as it lacks an organizing principles in terms of which to understand family replication, fermion masses, and fermion mixings. And here one should appreciate the legacy of oscillations. Oscillations have demonstrated not only that leptons mix, but also that they do so rather differently from the way quarks do. You have large mixing, and this cries out for a theoretical explanation. Likewise, there is another puzzle in the family sector, flavor problem, namely the hierarchies of the charged fermion masses. This is a very, very odd pattern indeed. These masses are not on scale, and it is very difficult to make sense of them. So nobody knows how. However, one interesting statement can be made, and that is, from the legacy of oscillation, in trying to understand the structure of the lepton mixing vis-a-vis the quark mixing, one has come about a whole bunch of new theories of flavor, here indicated in black. None of them is good enough that you can say, aha, this is the theory of flavor. But all of them are interesting. But perhaps more interesting is the fact that all of them, however different they all converge into this beautiful bottom tau flavor-dependent unification formula, which is rather successful, and I call it golden mass relation. And I believe that this golden quark-lepton-mass relation does form an ingredient of an ultimate theory of flavor. On the other hand, at this point, I should also stress that perhaps the complexity of the flavor problem is so huge that we could perhaps abandon the confines of four-dimensional gauge field theory. And this is an example of what flavor dynamics, as suggested by Lisa Randall to explain the gauge hierarchy. In fact, it can be upgraded, why not, to explain all of the Fermi mass hierarchies, whose explanation would be geometrized in a sense. That is far from being a practical explanation for a phenomenology, but it may be interesting for theorists. On the other hand, and more close to phenomenology, the mixing angles can be explained by family symmetries using our usual tricks, namely the imposition of a family symmetry. And it has been shown that the imposition of family symmetry is completely consistent with warping and able to give very simple analytical prediction for the mixing angles, as you see here, the tri-maximum prediction obtained from this model. And the predictions are very interesting. You see here on bottom, a very tight correlation between the magnitude of CP violation and the atmospheric octant. And on the other hand, you see here on top, the explanation for neutrinoless double beta decay will lie in these blue and red regions, and they are fully covered by the sensitivity of the upcoming round of experiments. This is for the case of warped flavor dynamics with 5 dimensions. We can go 1 dimension higher to a 6-dimensional orbifold. Here everything is flat except the singular points. And in this case,
can you conclude?
One has a unique feature of predicting the nature of the family symmetry, and that by itself predicts our beautiful golden quark mass relation. It predicts the sign of CP violation in oscillation, and it predicts the neutrinoless double beta decay amplitude. So, to make it short, extra dimension provide a very interesting framework for understanding flavor. So, since I was a bit cut in the magnitude of the talk, I will conclude mentioning that we are in a thriving moment for experimental neutrino physics, which aim to probe all the unknowns in neutrino oscillations, also many double beta decay searches, which aim to probe the Majorana nature. We have also something new, namely coherent elastic neutrino nuclear scattering has been discovered, and this provides a new probe of neutrino physics. And on the theory side, there are many items, which I list here, where neutrinos can play a key role. And these are drawbacks of particle physics to which neutrino can provide the answer. Thank you for your attention.
We can take only one question. I'm sorry. Okay, so please be short.
Sorry, what is the question?
Right. So I hope you can hear me, Jose. I'm Apostolos Pilaxis.
Yes.
I'd like to say that the radiative inverse seesaw was discussed in 2016. The scotogenic mechanism was discussed in 1992 by myself, okay? 14 years later, it was reinvented in a physics double model by Ernest Ma, right? So I hope the radiative seesaw and the low scale and all the technology people played with that, and it would be useful for you to look at these references as well.
Okay, thank you. Unfortunately, the talk was a bit fragmented because of this problem.
Hello, Jose, this is Paul Frampton. I'm sorry you're not here. Can you hear me?
Yes.
You mentioned the quasi-degenerate solution, and I just wanted to understand the numbers. So in cosmology, the upper limit is something like 100 milli-electron volts, but in the particle theory, degenerate, quasi-degenerate, would have to be bigger than that. Is that the problem? It would have to be 120 or something.
Well, I mean, basically, it comes from this bound, which is 120 milli-electron volts. However, one should, yes, it comes from there, and that is what leads to this vertical band here. What is different is that this is a new presentation of M beta beta, not versus mass, but versus this degeneracy parameter, which is suitable to this case, the same way as this parametrization is also a different parametrization versus the Majorana phase, which is suitable to the case where one of the neutrinos is massless or nearly so. In this case, these parametrizations are cleaner for the situation at hand. Of course, in general, one has this.
Okay, so let's thank our speaker. Thanks a lot. And now categories. Yes. Do we have a category, you see, which is who is connected?
Yeah, it's here. Can you hear me?
Okay.
Yeah, can I share my slide?
We are slightly behind schedule, so please try to be in time. You see, you've got 25 minutes, so this is maximally what we can allow given our schedule of the boat departures.
Yeah.
Please go ahead.
All right, let's try to see how I can share my slide. All right. Oh, it's here, Acrobat Reader.
Hello.
All right, can you see me?
Yes, indeed.
All right. Yeah, thank you for invitation, and I'm sorry I couldn't make it. And I know there was an excursion right after this, so I tried to make it really short. My name is Tepe. I'm from King's College, and this talk is about the test of fundamental physics with neutrinos. Okay, so what is fundamental physics? I mean, it's this. Well, it's an unlisted, limited list, but I just saw a few examples. So these are fundamental, and people believe, it's always true, but there's no reason to be true unless you test it by experimentally, and you have to test it by experiment. So such as spin statistics, Lorentz symmetry, Poincare symmetry, and CPD symmetry, and so on. And we believe these are true because it looks, they agree with the experiment. So the vibration, if they exist, must be very small. And also these are fundamental physics, which mean it's not easy to violate because you have to, reconstruct everything from scratch, but you can violate by effectively, not intrinsic violation. And people like these violations is because those could be an indication of some kind of ultra high energy theories, such as string theory or these things. So it's interesting to test these fundamental symmetries. And this is one example of spontaneous Lorentz symmetry breaking. How can be a Lorentz symmetry could be broken? So the SSB in the particle physics can be explained by this spontaneous symmetry breaking of a scalar field. And then this vacuum is saturated by a vacuum expectation value And that's a way to explain the mass term, because the mass term violates the gauge invariance. But in this way, your fundamental theory doesn't violate the gauge invariance, but in an observable level, it's broken. So it's similar things could happen for high energy theories, such as string field theory. So the one of the cubic term of a vector field, if they make SSB, and then the universe could be saturated by the vacuum expectation value of a vector field. And then in this way, Lorentz symmetry is broken as an appearance, but fundamental theory is not broken. Okay. So the coupling of standard model with these new physics might modify the behavior of standard model particles in vacuum. So the course of this work is to look for some new effect in the vacuum. Those include like matter antimatter asymmetry, direction-dependent physics, and modified dispersion, etc. But effect is expected to be really small. So we need some kind of high precision measurements to find this effect. So the effect we are talking is such as quantum form or some Lorentz violating field, which is basically ether. Just a brief overview of the history of the Microsomal experiment. So these are started from 19th century, and now the precision got more than 10 billion times better than the Microsomal. And the technology also swapped. It used to be an interferometer, and now it's a cavity test. And this is the snapshot of 2015, but it's getting even better. So yes, people keep testing these things, experimentally. So you need a high precision, and why use neutrinos? Because neutrinos in the particle physics, it's a kind of a lowest precision experiment, I would say. The reason is because this unusual properties of astrophysical neutrino. So those are the highest energy particle propagate straight. That's it. And also the propagation distance over 100 megaparsecs. So these neutrinos are useful to prove any tiny effect in the vacuum in the universe. So if something happens along this path on 100 megaparsec or even longer, propagation, the gigaparsec order, it's a tiny effect could be modify the property of neutrinos, such as energy spectrum or, flavor. So flavor is the topics of this talk. So these are a list of some effect. Oh, by the way, I have a slide uploaded. So if you have a Zoom link, I put it on the chat window. That's a talk of my slide of my talk. Okay. The way to see the astrophysical neutrino, you need a big detector because the flux is so low and the cross section is so low. And IceCube is the only one experiment so far succeeded. So these are array of photomultiplier tube under the South Pole ice. And it's roughly 1 kilometer cube. So the footprint is roughly kilometer square, this hexagonal shape. And this one is located below 1.5 kilometer to 2.5 kilometers. It's an array of photomultiplier tube. It's a 10-inch PMT. And this PMT is enclosed by the glass shell, which is called the digital optical module, because they're the front end board as well. And you drill the hole and you put one by one like this way in the picture. They don't look very cold because we always work in the building. So when it drills the hole, there's a housing in it and the people work it. And also this already happened in the summer of the South Pole. So these are event display for IceCube. Well, it's also from simulation. But so each dot represents the hit of photons, and the color shows the timing, and the size of the dot represents the amount of the charge, amount of photons. The topology you can measure is it's a bit poor comparing with other experiments. So for example, we call track is a muon neutrino cis interaction where muon neutrino makes a muon track. And this muon track makes the long trajectory. By the way, this is like kilometer, right? So it's quite long. But most of the interactions makes this kind of shower called cascade, such as new ECC, new tau CC, or neutral current. And you can't really tell, it's a big blob. So it's easy to measure the energy, but it's not easy to measure direction. And also it's not easy to differentiate the flavor. The tau has a special case. This is called a double cascade. where the production of the tau and the decay of tau makes a two shower. But in order to see it, this tau have to propagate long enough. You have to propagate like a 50 meter, it takes roughly 1 PeV. So only very high energy tau can do this. All right. Okay, and this is the observation. I think someone has to turn on the microphone.
Yeah, if you turn the microphone, please, because there is some noise.
All right. Yeah, let's assume it's done. So these are the recorded data. The black one is the original data from 2013, and the 2018 we updated. That's the new red dots. So the energy go all the way to the 2 PeV, 2000 TeV, from 60 TeV to 2000 TeV. And this is the declination directions. Okay. And so the most of them coming from the southern sky, which means the top. The reason is because when you pass the 50 TeV, neutrino even can't propagate the Earth. Okay, but we always talk neutrino is is a ghost particle. But in the 50 TeV, that's the end of the ghost particle. So they can't penetrate the Earth very well. So the most of the high energy neutrino coming from the sky. All right, and these are three famous ones with name, BERT, Ernie, Big BERT. And we stop using these naming. So now using these neutrinos to do some physics. Okay, so these high energy neutrinos are useful. And by looking at their properties, you can look for new physics, such as spectrum distortion, by some vacuum effect, or modification of time of flight, or some kind of a new mixing. So the idea is the following. So the Cherenkov radiation doesn't happen in the vacuum, but if there is some new field saturating the vacuum, you could make a Cherenkov radiation in the vacuum, and that modifies the spectrum. So that's a way to look for this kind of new physics. This is interesting because a similar effect in a CMB, now you can expect a polarization modification or rotation of a polarization plane in the vacuum. It's called the vacuum Bioregions. And there is some weak indication there may be some vacuum Bioregions for CMB. And that's corresponded to the physics of a scale 10 to minus 43 GeV. That's quite a high energy. Although these authors are not quite convinced this is not. The time of flight. So if you have a known source of a neutrino and photons, like astrophysical object, by looking for their time arrival difference, you can look for some new physics effect by the delay or sometimes advanced because of this new physics. There are many similar analyses, but the one by Ma et al. Is kind of interesting. So this kind of CPT order effect has a sign change for neutrino and anti-neutrino. And ice cube, we can't really tell. So you can assume each one is maybe neutrino or maybe anti-neutrino. And what they did is they can put everything nice along the one line. So assuming a certain neutrino to be anti-neutrino, so the sign flipped. And they extracted this new physics scale for around 10 to 17 GeV. So that means like some neutrino, so IceCube couldn't identify it's a point source from some transient event, but they're expecting some delay or advanced. They're adding extra time difference, assuming there's some new physics. The topic I want to talk today is this flavor structure. The reason is because if you look for the flavor, you can also include some kind of a quantum effect that enhance the sensitivity to look for small effects. So this is a reason astrophysical neutrinos are, neutrino experiment is not high precision, but it is in fact very competitive, even comparing with some tabletop experiment. The framework we use is this standard model extension motivated operators for Hamiltonian. So SME is an effective field theory to look for Lorentz. So you have a standard model term and you adding new terms, which is describe the coupling with the vacuum. And you can write down the Hamiltonian from here. And this one go on and on. So you can have an infinite series. But the things important for IceCube is this higher dimensional operators. Because these have a higher energy dependence. And my theorist colleagues said these are important. So I don't know really. And the dimension 6 operator is especially we focused, and there is some natural scale for this. The natural scale we assume is something inverse square of Planck's mass. And this is totally impossible to achieve by any particle physics experiment. So we tried this idea from atmospheric neutrino first. So the idea is the same, and the atmospheric neutrino is already the highest energy beam on the Earth. The maximum go to 20 TeV, actually even go higher, but above 20 TeV is a bit unclear. So we made a cutoff 20 TeV, and they propagate 10,000 kilometers. So it's the biggest interferometer, if you call it. And any spectrum distortion could be some new coupling, which is described by these terms. So and in this way, we try to extract possible extra coupling. And now you see the data and the expected effect. So yeah, you see we don't have any Lorentz violation, looks like. But the limit we extracted is down to 10 to minus 36 GeV inverse square, which is pretty close from our target goal, which is the square of the Planck's mass. And if you compare with the other field, this is not so bad. So if you look for a lower dimension, like a dimension 3 and a dimension 4, the tabletop experiment is better. And especially the famous one is this, the co-magnetometer. And this co-magnetometer is known to be a very high precision. It's called 10 to minus 34 GeV. Okay. Right, and these dimension 4 is also these co-magnetometer. But if you go to higher dimension, the leading experiment is our astrophysics. And ultra high energy cosmic ray is always good, and some of other astrophysical measurement is good. But our limit is comparable, just with atmospheric neutrino. So if we move to the astrophysical neutrino, maybe you can beat them. And I think that's true. So this is a sensitivity plot for a different field. So IceCube is best in neutrino. So we have we don't compare with other neutrino. So only our competitor is other field, such as OJ, ultra high energy cosmic ray. So 0 is normalized with the Planck mass, and we only care higher dimension in this case. And the dimension 6 is interesting because dimension 6, our sensitivity go beyond what we expect from this Planck mass natural scale, so the inverse of Planck mass square. So our sensitivity go above that. And if we go dimension 7, then we are still the best experiment comparing with other field, but our sensitivity looks not from the natural scale of Planck mass. So that's why we also focus on dimension 6. And the dimension 6 is also the lowest scale for new interactions. The good example is the Fermi constant. So that's message. And now moving to the astrophysical neutrino. Okay, so we want to use the astrophysical neutrino flavors, and the problem is we don't know the source composition of astrophysical neutrinos, and that's and also the statistics is low. So the tool we use is so-called flavor ratio, and so this is like a color triangle. This top is a muon neutrino, and the bottom right is electron neutrino, and the bottom left is the tau neutrinos. So by weighting the flux spectrum, your astrophysical neutrino measurement can be described one point in this phase space. Okay. And the production, the most likely production is some combination of electron neutrino and muon neutrino. So this yellow one, the pi decay, like electron neutrino to muon neutrino to tau neutrino, is 1 to 2 to 0 ratio is likely, although we don't know. And some people said, oh, maybe everything is electron neutrino, or some people say maybe everything is a muon neutrino. So we don't know. It's something along this line is the old solution. Everything with the tau neutrino is a bit exotic. So I call it exotic solution. Okay. So these are production model. However, that's not what we detect on the Earth because of the mixing. And the mixing happens without any new physics, just because they have mass and, it's a superposition of, different state. And these are what you expect on the Earth. So if you are muon neutrino dominant from top corner, you end up with this red distribution. And if you are only electron neutrino from the production in megaparsec away, you end up with this green bulb in some ways, real solution. And the size of this bulb is made by the error of oscillation parameters. So in this sense, if the oscillation experiment improve, we can narrow down the possible astrophysical neutrino flavor ratio. Okay, and same logic for yellow and blue. Okay, and if you combine all of them, this is gray band. So this gray band, now I ignore tau neutrino production model because there's no such model exist. So this gray band is the combination of any possible astrophysical models, which is a combination of electron neutrino and muon neutrino. And what you notice is it's a really small area comparing with this whole triangle. So if you see your flavor ratio on the Earth is outside of this gray band, that is already interesting. That's already telling some new physics. Of course, we don't know if the Lorentz violation or could be local effect, who knows, but it's interesting. And now let's adding some interaction with the new field and see what happened. So that's this one. So this is the field, the phase space, including a new physics, which is a new operator in my formalism. So new operator just below the limit of experiment. And what this said is we can generate any flavor ratio with new physics. And with, of course, new physics, it's not constrained. So yeah, astrophysical neutrino has a best sensitivity to look for new physics with the neutrinos. All right. And now moving to result. So the IceCube new flavor ratio result was published 3 years ago. Well, sorry, box opening was 3 years ago, and it's really published last year, I guess. Well, it's not 2011, it's a 2020 or something. I'm sorry. No, sorry. So it's a 2020 November. Yeah, that's right. Yeah, so this is the data. And what you notice is this size of the contour. So this 95 contour encloses all this area, and all possible flavor ratio from the standard model are inside of the contour. So that means if you have a tiny deviation from the standard model, you can't really see it. So on the other way to say it is the data is just consistent with everything. So we are not looking for we didn't see any new physics from here. However, there are a few regions outside of these contours. So there may be some new physics which predict your flavors on the Earth is all muon neutrino or all tau neutrino. If there's such model exists, they could be rejected. So that's a focus of this stage. Current statistics and systematics, that's the only things we can do, and that's what we did. So this is a result to be published this year. So the exclusion is the function of assumed flavor ratio, which is not the best scenario. So, and also the most of the exclusion coming from muon neutrino dominant scenario or electron neutrino dominant scenario, and the standard case, which is electron neutrino and the muon neutrino mixture, we don't have much limit. Nevertheless, we get some strong limit for a few cases, and these limits all go beyond what we expect some quantum gravity physics. I don't know, like a square of Planck scale for the case of dimension 6. So the goal for next goal for IceCube is to cover all area and also test all operators, because this limit is also given only for certain operators. All right, and my last slide. So how do we improve? Well, the IceCube is too small, so we need to make it bigger. So we have a plan to make it 10 times bigger, IceCube Gen 2. In the meantime, we are trying to improve this particle identification algorithm, because that's a key to measure the flavor ratio. Okay, so I'm sorry, I'm rushing too fast, but the take-home message is the search of quantum gravity motivated effect in IceCube, and we have a I believe we have a sensitivity to look for it. So this is not, I'm not fun to set the limit. We want to find it. So the next generation measurement, hopefully you can find it. All right, thank you.
Thank you very much. So let's thank our speaker. You can probably still take one question, even if you are slightly late. Is there any question from the audience? Oh, so there's one question coming from Zoom.
Yeah, can I ask the question now? Yes. Very nice talk, Tepe. Thanks very much. I would like to ask what you mentioned about the MA approach. How can you distinguish whether it's a neutrino or a neutrino in the present ice cube? That's what I missed. Or you're planning, or you're talking about the future.
Sorry, maybe I don't understand your question. Could you repeat one more time?
Sorry. Ma, you mentioned in a slide, you show Ma. Mass
this one,
whether because if you have a CPT violation, you have precisely this, a difference between neutrino and the neutrino. In the ice cube you cannot distinguish at present, am I right? That's right. Can you in the future, would you, that's what I was asking, would you be able to do that in the ice cube too, or
So this can be done only for the very special case. The famous one is the glacial resonance. The glacial resonance only for anti-electron neutrino. So using this trick, but the rest is all simulation, because experimentally now you cannot.
Right.
Especially high energy, the cross section is the same. So
right. Thanks very much. Thank you.
Thank you. So that means that we close our session. Thanks a lot to our speaker once more. For everyone who is here, the departure of the boat is in 25 minutes from now. In 28 minutes, yeah, from now. So please hurry up and go to the harbor.
How?